Kiri in reality me ja emena na dosavti ti omilia ti yati eleniki epitropi siragon ti yurti ti saya barbaras. Thank you everybody. Like, it's a great honor to be here. Maybe it's better in English. And so in my lecture tonight, I will try and illustrate the approaches that were developed to evaluate the effects of tunneling on the historical structures that were potentially affected by the construction of Line C of Roma underground. Now, in this title slide, I have put a picture which is one of the tunnels of Line B of Roma underground, as it is boldly constructed by cut and cover right next to the Colosseum. And this is a reminder of what was deemed acceptable in the 30s and is definitely not anymore, thus motivating the sort of studies that we've been carrying out in recent years about Line C of Roma underground. And before I start, I would like to acknowledge the fact that this work was carried out in close cooperation with my colleagues Sebastiano Rampello and Luigi Callisto from University of Roma La Sapienza, and also Fabio Soccodato from the University of Cagliari. So let's take a look at the line. This slide shows the route of Line C of Roma underground. Once completed, it will run northwest to southeast of the city center and then reach out to eastern suburbs of Roma for a total length of more than 25 kilometers and 33 stations. The tender for detailed design and construction of the line was awarded in February 2006, and the value of the tender was about 3 billion euros, making Line C the most important single civil engineering work in Italy currently under construction. Now, the line is divided into 7 contracts, as it's indicated in this slide, and the easternmost part of the line between Montecompre, Tripantano and Giardinetti is on surface, while the remaining part of the line is to be constructed underground using 2 EPB shields of a diameter of 6.7 meters. Now, the first part of the line, down to Lodi, was completed in 2014 and is currently fully operating, while the next stretch of the line between Lodi and Coliseum is currently under construction at different stages of advancement. In fact, San Giovanni station is nearly completed and it is going to be ready for use at some point next year. So they were actually hoping to have it up and running by the end of 2015, but now this has been postponed by about 6 months, while it is expected that to complete the remaining part of the line between San Giovanni station and Foro Imperiale Colosseo, it will take about another 5 years. So this is an aerial view of the central part of the route, consisting of about 5 kilometers of twin running tunnels and 6 stations, namely San Giovanni, where there is an exchange with the existing A line, Ambaradam Ipponio, Foro Imperiali, where there is another connection with the existing B line at Colosseo, Venezia, Chiesa Nuova and San Pietro. Now, this central part of the route falls under 2 contracts. So we have contract T3 between San Giovanni and Venezia, and then contract T2 from Venezia towards the Tiber River at San Pietro. These 2 contracts are quite different, completely different. Contract T3 is also called the archaeology contract because most of the monuments that are affected by construction of the line are Roman monuments dating from between the 1st and the 5th century AD. And right at the beginning of the contract, we have 2 important gates into the Aurelian walls that are Porta Metronia and Porta Sinaria, both dating from the 3rd century. And then further down the line, the Church of Santo Stefano Rotondo from the 5th century and the Amphitheatro Flavio, which everybody calls the Coliseum, from the 1st century. And the Basilica di Massenzio, which is a very important landmark in the Roman part of the city, from the 4th century, and several monuments along the Via dei Fori Imperiali, mostly dating to the 1st century. When we arrive at Venezia, the built environment changes completely because we leave the Roman part, the archaeological part of the city, and we enter into Renaissance Roma. So here we have a high density of very important masonry buildings that were built between the 15th century and the 18th century mostly. And all the areas that you see in this slide that are shaded in light blue were buildings for which the superintendent required a specific study to be carried out to make sure that the line could be constructed safely without damage to the buildings. Now, there are far too many to look at all of them, but just to give you a flavor, right at Piazza Venezia we have the last monument from the Roman age, which is the Colonna Traiana from the 2nd century, and then the beautiful church of Santa Maria di Loreto from the 16th century, the Vittoriano, which is a massive masonry building that was, the Romans called it the typewriter. They don't like it very much. It was built by the Savoia king at the end of the 18th century as a landmark of the new monarchy coming to Italy. And many buildings like Palazzo Venezia, which is very beautiful, and the Church of San Marco, the Palazzo Graziano. Further down the line towards the river, the Palazzo Sforza Cesarini, the Palazzo del Banco di Santo Spirito. So a very high density of very important buildings that need to be dealt with quite carefully. This slide shows the soil profile and groundwater conditions along contract T3. This is the archaeology contract. And if we start from the bottom, we recognize a base layer of stiff, over-consolidated silty clay, which is known as the Monte Vaticano clay from the Pliocene, which is overlain by sand and gravel. Above the sand and gravel, you can find either the sandy silts and clay silts of the Paleotevere or the more sandy unit of the Valle Giulia unit. They are both from the Pleistocene, and the Valle Giulia unit is the pink areas in the slide. Very occasionally there are some pyroclastic deposits, the light blue TA, labeled TA, like in the area of the Celio, and you can see that the Pleistocene deposits presents very frequent and deep incisions that correspond to ancient ditches towards the Tiber River, and these were filled by alluvial silty clay and silty sands. Above the natural soil deposits you have a very thick layer of made ground, and which in some areas can reach thicknesses of more than 20 meters. Of course, we are in central Roma, so made ground means archaeology. So this is forbidden ground. It is not wise to tunnel into the made ground. And you can see that the tunnels were placed almost everywhere at depths between 25 and 30 meters to avoid direct interferences between the line and the archaeology. But this means that on contract 3, the tunnels will run mostly through the coarse-grained and medium-grained deposits of the Pleistocene and well below the groundwater table. When we enter contract T2, we have a totally different geological profile. So corresponding to Piazza Venezia, there is a sharp discontinuity in the roof of the stiff over-consolidated clay. And so we found again a base layer of stiff over-consolidated clay, the Monte Vaticano clay. Again, on it we have sands and gravels with a thickness of about 10 meters. But this time these units are about 60 meters below ground level. And above them you find a very thick deposit of alluvium, which is from the Holocene. On top of it, again, we have made ground, so archaeology. The groundwater table is at about 8 meters below ground level. That is more or less at the contact between the made ground and the natural soils. And the alluvium is either fine-grained, which is the green and grayish areas in this slide, or coarser, like silts and sandy silts, which is the brown and orangish colors. So you can see that the tunnels run at the beginning and towards the end of this contract, they run into fine-grained layers, while towards in the middle of the contract, they run in coarse-grained layers. Now, this is a more detailed plan of the Renaissance part of the route, so this is what I'm going to talk mostly about in this presentation tonight for reasons of time. And based on the results of all the geotechnical site investigation, in situ test, laboratory test, the geotechnical characterization of contract T2 was subdivided into 3 zones, which are called A, B, and C. I mean, I guess could be 1, 2, 3, whatever. Anyway, and that are quite homogeneous from the point of view of the soil profile. So here here there is an indication of the typical soil profiles in zone A, B, and C. In fact, in zone B, which is more varied, I have two typical borehole logs, and then an indication of the depth of the tunnel. The fine-grained soils, which is either the silts in green immediately below the made ground and the silty clays, which are labeled AG in gray, are all normally consolidated. And as you can see, the tunnels run well into these silty clays at the beginning and at the end of the contract, while in the middle of the contract they run through sandy soils. Now, to give you an idea of the context in which these studies were carried out, it may be worth having a look at this flowchart that summarizes the organization of these studies of the interaction between the line and the tunnel. So the grantor of the line, that was the municipality of Roma through Roma Metropolitane Limited, required that the general contractor, that in this case is Metro C SCPA, should appoint an international multidisciplinary steering technical committee. This steering technical committee was addressing and coordinating the activities of 5 working groups that are listed at the bottom of the slides. And right in the middle of the working groups, there is this geotechnical engineering working group, of which I was a member, that was working in close interaction with all the rest of them, and particularly with the structural engineering group for this assessment of the potential damage to the buildings. Now, I will explain this better later, but this study was carried out with levels of increasing complexity. So at the first level, we did run some simplified analysis that were mostly based on semi-empirical relationships, assuming greenfield conditions, that is, completely neglecting the presence of the buildings. And at the second level of analysis, we did some interaction finite element analysis in which the buildings were included in the finite element mesh as equivalent solids that were fully embedded into the soil. And these analyses were run either in plane strain condition or three-dimensional conditions, depending on the case at hand. Now, the way the geotechnical engineering working group and the structural engineering working group were working together, cooperating, was like this. At the first level of analysis, the displacement field was computed by the geotechnical engineering working group using simplified procedures, so basically semi-empirical relationship. Then the displacement field obtained from simplified procedure was passed to the structural engineering working group, and they would apply this field of displacement to a 3D structural finite element model of the building. Then both groups would run independent evaluations of potential damage to the building, and depending on these independent evaluations, either the study was stopped at level 1 if we did not envisage any potential problem, or the building was passed to the next level of analysis. At this point, an equivalent solid had to be defined to represent the building with its stiffness, and this equivalent solid was inserted into a geotechnical finite element model, so a new displacement field taking into account the stiffness of the building and the weight of the building was computed by the geotechnical engineering working group, and then again the displacements were passed on to the structural people, and these displacements were fed into 2D or 3D structural models of the object. Could be a building or a monument. Again, the two groups were running independent evaluation of damage, and depending on the result of this independent evaluation, either the building was deemed safe or remedial measures were designed and implemented. Now, let's start from level 1 analysis. In this slide, I have tried to summarize the empirical procedures that we used in order to predict the greenfield displacement. So that is the displacements due to tunneling without considering the presence of the buildings. Now, this is based on the usual Gaussian prediction, so as most of you probably know, it is generally assumed that the displacement profile in a section orthogonal to the tunnel axis is well described by a Gaussian function, which is fully defined by two parameters that are the maximum settlement at the tunnel axis and the distance of the point of inflection from the tunnel axis I. Now, this distance of the point of inflection is related to the depth of the tunnel axis through a parameter K, which is the trough width parameter. And we assume the value of K at surface of around 0.4 to 0.5, and then we had the K which was varying with depth. And also the typical volume losses we were assuming were either 0.5%, which was the most likely scenario, and 1% like the worst case scenario. Remember that the tunnels are constructed using an EPB shield, so we're not expecting very large volume losses. Now, in order to take into account variations in the tunnel direction and also variations in the elevation of the tunnel was subdivided into rectilinear portion, and each portion was further subdivided into segments, each segment being at a constant depth. Then the displacements of each segment were computed as the difference between two tunnels of semi-infinite length, and total displacements were computed by superimposition of the displacements obtained for each of these segments. Now, all the displacements and strains were referred to a system of global coordinates x, y, and z, and then the horizontal strains along any given alignment could be obtained rotating the strain tensor in the direction you needed. Now, to give you an idea of what we were doing with reference to a specific case, this is Palazzo Grazioli, so this is one of the buildings that we had to look at. This is quite famous because it's the Roman residence of Mr. Berlusconi, so it attracts a lot of public attention. And this is the building. It has, these are two pictures of the two facades on Via del Plebiscito and in Piazza Grazioli. And these are the settlement contours that were simply computed by a Gaussian prediction at an elevation of 9 meters below ground level, that is the depth of the foundations of this building, for an assumed volume loss of 0.5%, as the first tunnel is progressively advancing and the second tunnel is progressively advancing. So we can consider intermediate positions of the tunnel phase. And this is a section more or less orthogonal to the tunnel axis, where you can see the final displacement, vertical displacements that are computed immediately after construction of the first tunnel, and this is the red and green lines, and immediately after construction of the second tunnel, which is the blue and black lines, for two values of assumed volume losses of 0.5% and 1%. The maximum settlement due to the construction of the tunnels is in the region of 7 millimeters, and or 14 millimeters if you consider a volume loss of 1%. And there is very little interaction between the two tunnels in the sense that they are quite far apart. So most of the building is deformed in hogging, with a minimum settlement in between the two tunnels, which is of the region of 2 to 4 millimeters, depending on the volume loss you are assuming. Now, this is very simple. I guess this is common practice when you do your preliminary evaluation of the effects of tunneling. But we moved on towards level 2 analysis, where we wanted to consider soil structure interaction. So at this point, there are several things you have to consider. First of all, the soil has got to come into the picture, so this is not got to be represented solely by parameter K, which is telling you all about the soil, but you want to look at the actual soil profile, pore water pressure regime, geotechnical properties, so mechanical properties of the soil, and also you want to choose a constitutive model which is capable of interpreting properly the behavior of the soil. Then you have to simulate with numerical analysis tunnel construction, so you can do that either in 2D or 3D. You have to model tunnel excavation, and then you have to take into account potential long-term effects due to seepage towards the tunnel. Finally, you have to take into account the buildings, which will come into the picture with its stiffness, with its weight. Remember that these are quite heavy buildings, masonry buildings, and also with the fact that it's not simply resting on the ground, but it has an embedded depth of foundation. And this was done through the introduction of this equivalent solid. So let's look again at Palazzo Grazioli. We'll use it as an example. So this is a section through Palazzo Grazioli with the actual soil profile. We are in Zone A, very close to Piazza Venezia. So here the soil profile is relatively simple. We have about 10 meters of made ground, followed by about 46 meters of silty clay, and then 10 meters, 5 to 10 meters of gravel, and then the stiff, over-consolidated silty clay, which is the base layer. The tunnels are at a depth of about 28 meters below ground level, and the groundwater table is 8 meters below the ground level, so pretty close to the contact between the made ground and the natural soil. Now, the soil behavior was modeled using elastoplastic isotropic hardening model with more Coulomb failure criterion and two yield surfaces, one deviatoric yield surface and one volumetric yield surface. Both of them are hardening. The hardening is isotropic and depends on the plastic, deviatoric, and volumetric strains. The flow rule is non-associated for states, for stress states on the deviatoric yield surface, and is associated for states resting on the volumetric yield surface. The elastic part of the model is isotropic elastic, but with a pressure-dependent Young's modulus, according to the formula which is in this slide. And because E dash is the initial stiffness of the soil, this was obtained, the behavior of this model is non-linear right from the beginning of loading, and also you have irreversible strains right from the beginning of loading. So despite the fact that this is a commercial model, it's not anything particularly complicated. We chose this one because it was included in the libraries of the two commercial codes that are Plaxis and Toknog that we were using for the analysis. It is relatively simple, but can account for most of the features of the mechanical behavior that we need to include into our analysis. Now, because E is related to the initial stiffness of the soil, we obtained this parameter from some cross-hole tests that we had measuring the shear wave velocity and hence the small strain shear modulus of the soil. And here you can see the results of 3 cross-hole tests that are the colored dots, together with some laboratory tests done either with the resonant column or in triaxial cells equipped with Bender elements. You can see that there is a very good agreement between field measurements of small strain stiffness and laboratory measurements of small strain stiffness. And the continuous gray line going through the experimental data is the calibration of the stiffness profile that we obtain using this small strain model with the parameters that are reported in the slide. So it was calibrated against the experimental data on site. As far as the effective stress shear strength parameters are concerned, they were obtained from drained and undrained triaxial tests. And you can see that the behavior of the silty clay, that is the most relevant layer in this case, is essentially contractant and ductile to failure. So this is normally consolidated clay. If you take a look at the initial part of the stress strain behavior, the nonlinear behavior of the soil is described using these other two parameters that, although they are called E50 and E odometer, they have nothing to do with elastic properties. They are in fact related to the hardening rules of the hardening soil model. And you can see that the agreement between the experimental data and the model prediction, particularly at small strains, is quite good. So we decided that this model was good enough to model what we needed to model. Then we have to simulate tunnel construction, and this will have to be done either in 2D or 3D. So the plane strain analysis, there are standard techniques to model tunnel construction, and they are either based on the partial removal of nodal forces. This is typically done by some reduction factor lambda, or you impose ground movements to the excavation section. And this can be a homothetic contraction of the section, which is typically done keeping the invert fixed and then contracting the section in a smaller circle. And the field of displacement is completely defined by this delta parameter, which is the maximum displacement at the ground. Once you have either reduced the nodal forces or imposed this field of displacement, you install the permanent lining, you release the conditions on forces or displacements, and then you let the system find a new configuration of equilibrium. And then you can change either lambda or delta in order to obtain a prescribed value of the volume loss at surface. And if you do this, you can get a reasonable agreement with the overall volume loss. The black line is the Gaussian prediction, so it's based on experimental data. It's supposed to be good enough, while the blue and green lines are those obtained with uniform unloading and or uniform contraction of the tunnel section. And you can see that the overall volume loss is okay, but the type of settlement profile you obtain is wider than observed in practice, and also the maximum settlement and the tunnel axis is smaller than observed in practice. And so we decided to change slightly this technique, using a particular field of displacements where the invert was kept fixed, so we didn't apply any displacements at the bottom part of the gallery of the tunnel, and instead we were applying a displacement field just to the upper part of the tunnel, so only at the crown. Again, also this field of displacements is fully described once you fix delta, and in this case we could get a much better agreement between the numerical prediction and the Gaussian expression. So we were working like this. In 3D, what we did is simply a kind of extension to 3D conditions of this 2D technique. Basically, what you're doing, you are excavating the tunnel in steps, and so the whole mesh is divided in slices. In this case, there were 2-meter slices, and then you are advancing the tunnel by 2 meters, removing the soil elements that are at the face. You keep a support pressure applied at the face. The area, the region next to the face is fully lined by the shield, and then you have 2 slices at the bottom of the shield that are not supported by the permanent lining, and this is where you apply the same field of displacement that you apply in 2D conditions. And then this thing goes on and on. You continue to move this kind of machine ahead to produce your displacement trough. And basically we're doing calibration of this model in 3D. You can see a typical calibration mesh where you have the stiff glaze and then the made ground. You can recognize the elements of the permanent lining and the elements of the shield, and we adjust the value of delta at the ground in order to get a volume loss of 0.5% at the ground surface, and also compare the numerical prediction with the Gaussian expression to make sure that we also have a nice width which corresponds to a trough width parameter of about 0.4. And then in the interaction analysis, we would keep the same value of delta. So we calibrate the model in Greenfield condition to get a good Gaussian prediction, and then we use the same value of delta to do the interaction analysis. Now, when you look at tunnels that are done in fine-grained soils, you also have to worry about long-term settlements. You might have some long-term settlements, and this is because you get some immediate settlement in undrained conditions immediately after tunnel construction, but then the tunnel is imposing a new drainage condition because it's never perfectly impermeable. It acts as a drain, thus reducing the groundwater pressure and then increasing the effective stress and creating long-term settlements. Now, Mer and Taylor reviewed what are the most important factors when you are trying to assess the long-term behavior in tunnels in clay. And they were listing in their paper that the important factors to look at are the initial pore water pressure distribution, the excess pore water pressure generated by tunnel, the compressibility of the clay, but most than everything else is the ratio of the permeability of the lining to the permeability of the soil, which is governing the long-term settlements. And as an example, Professor Meyer in his ranking lecture in 2008 was showing the long-term settlements of 2 tunnels of the Jubilee Line extension at Elizabeth House and St. James's Park. Actually, it's the Jubilee Line extension at 2 different locations. So the depths of the tunnel were comparable. They were both in London clay. The diameter of the tunnel was the same. The only difference between these 2 cases was the permeability of the lining. So at Elizabeth House, where you had sprayed concrete and then a permanent lining of sprayed concrete and then a permanent lining built with segments, concrete segments, so very low permeability lining, you only had over 11 years of monitoring, you had an increase of the settlements of just about 20 millimeters, While at St. James's Park, where you had 200 millimeters precast iron segmental lining without any grouting at the back, so it was a much more permeable lining, the long-term settlements arrived to up to 80 millimeters. So if we want to understand this better, it is probably worth looking at a very simple one-dimensional idea of this phenomenon. So here you have in orange, this is the soil, so it's one-dimensional seepage through the soil, and this is the tunnel lining with a thickness TL. Now, H is the hydraulic head at a distance L from the interface from the tunnel lining and the soil, where you are supposing that this is not affected by the tunnel anymore, while HE is the hydraulic head at the external, at the contact between the soil and the lining. Now, the value of HE in one-dimensional condition is given by this expression on the top, where parameter alpha, which is governing how much head loss you will have in the soil and how much head loss you will have through the lining, depends on the ratio of the permeability of the lining to the permeability of the soil, and also of the ratio on the drainage length in soil to the thickness of the lining. For a fully permeable lining, so if you are assuming that the lining is completely permeable, then alpha tends to infinity, and what you have is that the hydraulic head at the is fully dissipated within the soil. So inside the tunnel you have a hydraulic head HI, if you're assuming that the pore water pressure is 0, is atmospheric, and the hydraulic head will be fully dissipated into the soil. This means that you will have the maximum variation of effective stress and hence the maximum settlements. Of course, this condition is only attained as a steady state condition, so in the long term it will take some time before the seepage is like this. At the other end, if you have a fully impermeable lining, so you're saying the lining is completely impermeable, then alpha goes to 0, and then there is no head which is dissipated through the soil, and all the hydraulic head will be dissipated in the seepage through the lining. At this point, you will not have any variation in the effective stress, and you might expect very small long-term settlements. Now, some studies, parametric studies that were carried out to try and assess when you have to worry about long-term settlements, were indicating that you should worry about them when alpha is larger than about 0.1. In order to evaluate alpha, you need to know the ratio of the permeabilities of the soil and the lining. And of course, both these things are very difficult parameters to obtain. It's not that easy to say what they are. So as far as the silty clay was concerned, we were mostly looking at the results of dissipation tests for CPTU done on site, because of course the values of permeability you get from odometer tests are much smaller than on site. So you want to look at field permeability measurements. And they were indicating a permeability which was in the region of 6 times 10 to the minus 11 meters per second. So this clay is really not very permeable at all. As far as the lining was concerned, we used some seepage tests through the grouting that was done at the back of the segmental lining, and for the segmental lining itself we were using literature data, because the concrete is very little permeable, but then you might have imperfections in the joints, or maybe you might have some leaking gaskets. So we came out with some numbers. We took this ratio of K of the lining to K of the soil. Our best estimate of this ratio is in the region of 0.1, and then a typical drainage length, which was about 10 to 20 meters, which produces values of alpha which are 2 to 4. So yes, you have to worry about long-term settlements, because we were saying they are significant when alpha is larger than 0.1. Here we are at 2, 4. So some preliminary studies were done to assess the importance of long-term effects. This was done in Zone A and Zone C, where you have a significant thickness of the silty clay. In this case, the buildings were simply represented by loaded areas, so they had no stiffness, they were just applying a load at the surface. And we simply modeled one tunnel. And the drainage conditions at the tunnel were changed. So in the short term, we had the full impermeable lining, and then in the long term, the lining was modeled as a permeable material, setting to zero the pore water pressures inside the tunnel and looking at the consolidation. And this is the results. So you see the purple lines are the end of tunnel construction, so undrained conditions, and we get some settlements for zone A or zone C. And then the green lines are the long-term settlements, which are computed for a range of values of the ratio of K lining to K soil. I just want to remind you that our best estimate is K lining to K soil equal to 0.1. So it is this continuous green line here. And you can see that particularly in zone A, where you have the very big thickness of silty clay, 46 meters of silty clay, the long-term settlement is about 3 times the short-term settlement. It will, of course, develop in time. It's not something that is going to happen immediately. It needs to go to steady-state seepage, but it is there. And while in zone C, you still have an effect of long-term, but this is much smaller, because you have a draining layer of coarse-grained material only 4 meters above the tunnel crown. So it's not quite as critical as in zone A. So we know this, and we have to bear this in mind. Last ingredient we need to put in the level 2 analysis is the buildings, with their stiffness, weight, and embedded depth of foundation. And we said that we wanted to develop an equivalent solid approach. So what do I mean? Is that in the geotechnical finite element analysis, we needed to include not the full finite element model of the building, but this had to become a much simpler object. There was a 3D object that would be fully embedded into the soil. And these two things, the real structure with all the details, the opening, the walls and ever, had to be equivalent to this solid, which simply had a very rough shape. So when you say equivalent, you have to define a criterion for equivalence. So in this case, our equivalence was that these two objects should behave in the same way when you apply to it a given perturbation. And in this case, the perturbation was the green field displacement. So we applied to the base of the full 3D model and to the equivalent solid the green field displacements that we were computing for green field analysis, empirical procedures. And then we looked at the reaction at the nodal forces at the base of these two solids, and we were trying to make them fit. Now, the equivalent solid has a given geometry, it is fully embedded into the soil, and it is assumed isotropic elastic. So once you are in this condition, the only thing you can change in order to make it behave in a different way is the equivalent Young's modulus. So the equivalent Young's modulus was changed to minimize the difference between the node reactions when you are applying a given perturbation to the node base. And then this equivalent solid was introduced into the geotechnical finite element analysis, and then the displacements were computed again. These displacements were passed to the structural people, and they would apply this new displacement field to the complete model of the structure. Now, of course, when you do this interaction analysis, there are some assumptions that you have to make. For instance, most of the cases we only considered the bearing walls that were orthogonal to the tunnel axis, so we were only considering the stiffness of the masonry walls orthogonal to the tunnel axis, not considering anything cladding in the other direction. And also you had to do some scaling of stiffness, because the first thing you had to do was to do a first scaling of stiffness to define the structural equivalent solid, which is just one facade. So we want to have one facade which has to become an equivalent solid, and you have to do a scaling of the stiffness to take into account the distance, the typical average distance between two following bearing walls. And then when you insert this into geotechnical plane strain analysis, you have to spread this stiffness, because otherwise you have something which is infinitely stiff in the plane strain direction. So again, to go to Palazzo Grazioli, because this exercise was done for Palazzo Grazioli, this is a plan of the building showing the two tunnel axes, and I want to show you some results relative to the facade on Via degli Astalli, which is this orange line here. And this is a section through the building showing that the depth of foundation is quite deep, it's about 9 meters below ground level. So first of all, we had to define an equivalence between the full facade, the structural model of the full facade, which was developed by the structural people. So they had different zones with different thicknesses, the openings and everything. And then this had to become a structural equivalent solid. So just a wall that should be inserted into the geotechnical finite element mesh. And in this thing, we were changing the Young's modulus in order to get the same distribution of node reaction at the base of these two objects. And the optimum value reduced the stiffness of the masonry from 2.5 gigapascal to about 3.9 gigapascal. Then, when you are doing 2D analysis, you have to spread this stiffness because you want to obtain a plane strain condition, and so this was reduced again to 1.2 gigapascal. When you did 3D interaction analysis of Palazzo Grazioli, of course in this case you have a 3D structural model of the building and you have to end up with a 3D model equivalent solid. And again we were doing this by looking at the resultant shear forces on some alignment along the building and changing the Young's modulus in order to minimize the difference between the two. And in this case, we went from an original stiffness of 2.5 gigapascal to a final stiffness which was slightly lower, 2.38 megapascal. And in this case, because the geotechnical analysis was 3D, there was no further scaling of stiffness. So this was the final value of stiffness that we had in the mesh. Now, I will compare the results that we obtained from Greenfield, 2D interaction analysis and 3D interaction analysis relative to one of the facades, which is the facade on Via degli Astalli. And also, I have this plan view just to remind you that in the 2D analysis, we are making some simplifying assumptions. So we are taking the facade to be perfectly orthogonal to the tunnel axis, which obviously is not. It's at an angle. It has a skew. So you've seen this slide already. This was the results of the semi-empirical predictions with 7 millimeters or 14 millimeters maximum settlement, very little interaction between the two tunnels, most of the building deformed in hogging. And this was referring to an orthogonal section through the building, which is the pink line here at the bottom. Now, these are the results from the 2D finite element analysis, interaction analysis. So the maximum, the blue line is at the end of construction of the first tunnel, the green line is at the end of construction of the second tunnel, and the orange line is taking into account long-term effects. So after you've let the new boundary condition at the tunnel boundary be effective. Now, the maximum settlement predicted by this is for an assumed volume loss of 0.5%. The maximum settlement predicted by the 2D interaction analysis is of the order of 10 millimeters, so the Greenfield prediction was 7 millimeters, is not very different, but the shape of the settlement trough is completely different. So, first of all, we don't have two separate troughs, we have one single thing, which is deforming mostly in sagging, not in hogging. So the settlement is rather uniform underneath the building with a little bit of sagging and much less curvature. And this is due both to the building's weight, which was not in the empirical prediction, and to the building stiffness. Of course, in the long term, you get a settlement which is about 2.5 times the short-term settlement. Now, this is the area of Piazza Venezia. So you can see this is Palazzo Grazioli here, in the middle between Palazzo Altieri and Palazzo Doria Pamphili, right opposite to Palazzo Venezia. So you can see that there are quite a lot of very densely packed, massive buildings. And here the tunnels are making a very large curve as they come into Piazza Venezia and then they enter the Via del Corso. So the situation is very 3D. So we decided we really needed to model this in 3D. It was not good enough to look at 2D. So we created a very large finite element mesh that was including all the equivalent solids that represented those buildings with their weight, their stiffness, and all these buildings were identified by this procedure of minimizing the difference to a given, of the node reactions to a given perturbation. They were all inserted into the mesh, and then the tunnels were excavated with that step-by-step procedure with their true alignment, with a big curve and a varying elevation. Now, of course, because this was a very, very time-consuming and very big mesh, we had to make some simplifications about the soil profile. So, for instance, here we put the groundwater table, which is in fact at 8 meters more or less below the ground surface. We put it at 10 meters, so exactly at the contact between the made ground and the silty clay. Also, we assumed that the layers were perfectly horizontal, and we fixed the bottom of the mesh corresponding to the roof of the sands and gravels. So it is relatively simplified, but includes everything it needs to include. And these are the results of the finite element analysis, showing the advancement of the first tunnel. This is at foundation level, so about 9 meters below ground level, as the first tunnel is advancing for an assumed volume loss of 0.5%, and then the second tunnel is coming in. And then at the end of construction, you get a settlement which in the region of Palazzo Grazioli is of the order of 11, 12 millimeters. So not very different from what we were predicting in 2D. You can see that here, where the tunnels are a little further apart, it is true that the two settlement troughs are not interacting, but here, where you have structural stiffness and you also have the weight of the buildings, the two troughs are in fact merging together. Then we let consolidation develop, so we allowed for the new boundary condition, drainage boundary condition at the tunnel, and the settlements increased. Now you have a maximum settlement of the order of 22 millimeters, and the trough width has increased to about 130 meters. So if we look again at the section through Palazzo Grazioli, this red line was the greenfield prediction for 0.5% volume loss. Maximum settlement in the region of 7 millimeters, in the middle of the building just 2 millimeters, and all the building deformed in hogging. The 2D finite element analysis were not predicting any hogging, so we had the whole of the building in sagging, while the 3D finite element analysis, because they contain also the weight of the neighboring buildings and the real geometry, they are predicting mostly sagging, but also a little bit of hogging on this side. What it is important is that relatively to the greenfield prediction, the horizontal strains on the masonry are much smaller, so you get practically no horizontal strains. So at this point, from the point of view of the geotechnical engineering working group, we have all the elements to make an evaluation of potential damage over L and horizontal strains, defining, limits where you have no damage, a little bit of damage, more damage, and so on. I must say that the values of strain at which one zone was dividing from the next zone were actually quite low, because we were trying to take into account the monumental importance of this building. So we were using quite low thresholds on the admissible horizontal strain. And here we are comparing the damage evaluation done using the greenfield, which is the red dots, both in sagging and hogging. And you can see that we are always more or less within zone 0 or 1. The only case in which we end up in zone 1 or 2 is in hogging, so towards the center of the building, in greenfield condition, and when we're using the maximum tensile strain rather than the average tensile strain. The 2D finite element analysis did not predict any hogging, so we cannot look at the hogging damage. We can only look at the sagging damage, but all the points are well within zone 0, so there is no expected damage. And the same is true if we look at 3D finite element analysis, particularly in hogging, where the red dot is the greenfield prediction and the blue, light blue dot is the 3D finite element analysis. Now, for us, this is a kind of an indication of potential damage. There might be some damage, and this damage is likely to be into this class of damage, but this is not telling you anything about where the damage to the building might be, and this was instead more the role of the structural people. This is the typical sort of results they were getting. So they were applying some settlements to the bottom of a very complex mesh of the building, and then looking, for instance, this is the greenfield settlements applied at the bottom of that mesh, and this is the results in terms of contours of maximum principal stress. If we look at the facade on Via degli Astalli, we can see that if we impose the greenfield displacements in the short term, we have quite a lot of important stress, And this is corresponding to quite a lot of damage, particularly around the openings at level 1 and level 2. If we impose the short-term settlements that are predicted from the interaction analysis, so they are much smaller because they take into account the stiffness of the building, the situation improves dramatically. You don't get any more all this stress concentration and this very dangerous situation. And what's more important is that if you look at the long-term conditions, so when you increase further the displacement, the situation improves. So the damage to the building is less, because despite the fact the settlements are larger, there is less curvature. The settlements are also more uniform, so the building is less strained by long-term settlements. So I might kind of stop here as far as Metro C goes, but instead I want to spend another 10 minutes to tell you something about this net-ton business, which is another byproduct, in a way, of Line C of Roma underground. So what is it? This is a large collaborative project which is funded by the European Commission through the 7th Framework Programme, and it involves a lot of people. It's 21 partners that are industry, research and development, and small-medium enterprises, and 9 European countries. And the general objective is to address a set of research teams that go to the construction, management, and maintenance of tunnels. So it's very wide. But nested within this large group of people, there is a smaller contingent, which is this work package 9, which is devoting their research efforts to evaluating the impact of tunneling on surrounding structures. And there are 4 partners into this work package 9, which is Università di Roma Tor Vergata, being me, plus the NTP Lyon in France, and also the National Technical University of Athens, with Michalis Cavades and his co-workers, and the contractor, the general contractor, Metro C SCPA. What we want to do is to develop properly a numerical procedure to study the impact of EPB tunneling on structures, because although what I showed you, this 3D numerical modeling of tunnel advancement, might sound really sexy, it is not really. It is something really simple you do with a commercial code, and it doesn't contain any of the physical processes going around the TBM. So it is just a, let's say, a settlement generator. It's something that, by imposing the field of displacements at the tunnel boundary, creates a set of displacements that look like the ones we observe in practice. But it's very non-scientific in a way. Also, we want to develop a method for the early detection of over-excavation at the tunnel face, which might be a very dangerous situation in the urban environment, and we want to evaluate the effectiveness of mitigation measures, and we are doing it using a combination of physical modeling, numerical modeling, and field monitoring. So, physical modeling is the NTP team in France, but these pictures are very impressive, so I wanted to have them here. And they have a model TBM. It is in a scale of about 1 to 10. It's a real EPB shield with everything, the screw conveyor, the conical excavation chamber and everything. And this thing advances in a big calibration chamber filled with sand, which is about 2 meters long, 2.15 meters tall, and 2 meters wide in the other direction. Now, this is not simply advancing into pure sand, but they are creating structures around the tunnel. So they are looking at single piles at different positions around the TBM, and also at little groups of piles. And I want to point at the fact that these piles are driven piles. They are driven into the sandbox, and then the load is applied on them. So while the TBM advances, the piles are actually loaded. They are under their service load. Now, this is to give you an indication of this. These are the 3 jacks, hydraulic jacks, that are keeping the load on the 3 model piles, and also the model is fully instrumented at surface and at depth to look at displacement, stresses, and a number of things, and also they're using photogrammetry, so particle image velocimetry at the surface to get the full picture of the surface settlement. And they're getting really interesting results. So now we are in a moment where there are a lot of results coming out. Some of them are very surprising, such as you might have some bending moments on the piles, also on the pile which is immediately above the crown, so you wouldn't expect any transverse bending of this pile, and instead you get some, and this is probably due to the rotation of the cutter head. So we're still looking into to this data. Now, this is not just done physically, we're also doing numerical modeling, and because this is research, we are trying to develop proper techniques to model with finite elements the main construction processes. So the left part of the slides refers to work done mostly here by Dimitris Litsas, Michalis, and all the co-workers, to look at all the physical processes happening around the TBM. So looking at the overcut of the cutter head, the shield tapering, the tail void, the fact that the segmental lining has joint contacts, gap grouting, a number of phenomena. And on the other end, and this is work done mostly at Tor Vergata by Nunzio Lo Sacco and other people working with us, we are doing alternative Lagrangian-Eulerian finite element modeling of the development of phase pressure and settlements. That is, you put yourself in a reference frame which is fixed on the TBM and the soil is flowing around you, so you are extracting the soil from the excavation chamber and are looking at the steady state displacements that result from this. This is more similar to fluid sort of modeling of these processes. And this alternative Lagrangian-Eulerian is mostly done to model the experiment. So it's mostly done to model the experiments that they are doing at NTP, while the other modeling, the finite element modeling, is to actually look at the effect of all a number of physical things, such as, say, I have extracted one picture, so I could show you more, the effect that the grout pressure for the tail void grouting has on the final values of the settlements at surface. So they're doing parametric studies of this with fully coupled Lagrangian analysis. And this has the aim, in the end, of remodeling the TBM tunnels in Roma for Metro C, and to look at the interaction with the relevant structures, such as the Mura Aureliana and Porta Metronia, which are going to be underpassed by the two tunnels. So we are kind of building up a tool which will be physically sound, well based in the physics, to try and predict the field displacement. But also, as a parallel activity, and here Michalis should talk about it because I'm still not sure I understand the details of this properly, this is done to develop a relationship between phase extrusion and TBM phase pressure and soil parameters that would tell you what is the normal functioning of the TBM. And then by looking at the rate of excavated weight, so the MAC weight on the train, and try and do some statistical analysis to detect early some over-excavation at the tunnel face, so that you can relate that to the possibility that you might be going towards a problem area early on, so you get a warning from the system. It's actually very interesting, and it's looking at the moment very, very promising. I said also field monitoring, and this is why this is Metro C. We have convinced Metro C SCPA to join us in this kind of research project. So we have two sections. This is the Netton stretch between San Giovanni and Porta Metronia, and we have two sites at Porta Metronia and at the Ama site where we are doing field trials of compensation grouting for Porta Metronia and greenfield control sections, plus field trials of barriers as other protection measures. And at the moment, we have bought all the instruments. We are deeply instrumenting Porta Metronia to have a look, have all the base readings before the tunnels will go by. This installation will be completed by December, so it's actually happening. And then we're also instrumenting greenfield sections, so to simply, in some areas at the Ama site where we don't have any buildings around, to get the greenfield behavior, and also looking at some protective measures such as barriers put to the side of the tunnel, and also compensation grouting, because the design specifies that at Porta Metronia they might have a mitigation measure where you insert a fan of TBMs between the crown of the tunnels and the foundations of Porta Metronia in order to compensate for any settlement. So before we do the real mitigation measures, we are planning to do a field trial in an area that we have nearby to see whether we can do this properly. So this has been a lot of fun, I must say. It's been now going on for nearly 3 years, and we've had many, many opportunities to interact We've been visiting sites, sharing knowledge with engineers on site. We've been brainstorming together. These are pictures in Athens. You might recognize the office, the Grafeo, near Michali's room, and this is another office in Roma. So we often get together and try and sort out all our problems together. And also we are taken to Rosalia, sometimes in the night. We have fun. We are enjoying each other's company. Now, concluding remarks. What was it I was trying to convey is that there are many cases, particularly in European cities, and I'm sure that Athens in this respect is no different from Roma, where you have to build a metro line through a very densely built urban environment, which might be historical but also not historical. In Europe, it is typical that the city center might be a small portion of the total built area of the city, but it is typically the one where the identity of the town is, where everything that is precious and we care about is. So we want to make sure we go through without damaging the surroundings. And it is often the case that you have many, many, many buildings to study. So you have to develop a handy but reliable procedure. So you can't really do a detailed study of every single object you have in sight. You have to have procedures that are reliable and handy, and we think that the whole process relies very deeply on the geotechnical analysis. So you have to have a very careful geotechnical characterization. Your site investigation has to be good. You have to use reliable models. You have to use levels of analysis of increasing complexity. So you shouldn't plunge into 3D numerical modeling of interaction every time you have a building. You might start from simple semi-empirical procedures and then do your evaluation and decide whether and when you need any more detailed studies. And also for us it was very important to have two independent evaluations of damage. So the geotechnical people were doing their bit, the structural people were doing their bit, but they were continuously communicating. Also, this type of projects require a lot of cooperation with other disciplines. So you have to look at building features and history. When you look at these historical buildings, you don't have a design deposited in some office. You have to find out where the foundations are, what is the likely state of the masonry, and so on. You have to have a very good look at geology. You have to talk to the structural engineer. You have to rely very heavily on monitoring. So you have to have a good monitoring plan. And also, I think that projects like this, like Line C or any other project, are great opportunities for research, for cooperation, and may I add, for friendship, because this has been a very nice experience to have. And that was about what I wanted to tell you tonight.